Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are doing a deep dive into a really crucial topic from Unit 3, current electricity. It's the Wheatstone Bridge. Our goal is simple, to explain this circuit so clearly that you lose all fear and really understand its amazing precision for life. So let's start with a simple question. Have you ever wondered how engineers measure something incredibly tiny? I mean, something a regular multimeter just can't see. Like, for instance, the minuscule change in resistance when a huge steel bridge stretches just a little bit under a heavy truck.
That sounds very, very precise. Measuring the resistance change from stretching, that sounds much more complex than just, using a multimeter on a resistor.
It is, and this is where it gets really interesting. A Wheatstone bridge is so sensitive that it's actually used in what we call strain gauges.
Strain gauges.
Yes, in dams, buildings, even aircraft wings. It can detect resistance changes as small as, say, 0.01%.
Wow, that's tiny.
It is completely invisible to the naked eye, and the whole point is that this circuit configuration is far more accurate than trying to measure that resistance directly. We aren't measuring the absolute value, we are measuring the ratio. We will unpack this.
Okay, let's unpack that. The core idea of the Wheatstone Bridge is that it's a special circuit. A setup of 4 resistors designed to measure one unknown resistance with, well, very high precision.
And how does it do that?
It does this by finding a state we call balance. It's a point where one part of the circuit has the exact same electrical potential as another part. Think of it like a perfectly balanced weighing scale, an old-fashioned one.
Okay, I can picture that.
Imagine 4 weights, these are our resistors, arranged at different places. When the scale is perfectly balanced, it's not tilting at all. That means the product of the weights on one side equals the product of the weights on the other. Our bridge is balanced when R1 multiplied by R4 is equal to R2 multiplied by R3.
Right, the opposite pairs. Exactly, and you might wonder, why does this method even exist? Well, it's because early meters were just not very sensitive. The bridge allows for a technique called null detection. It is much, much easier to precisely detect when a sensitive current meter, a galvanometer, reads exactly 0 current.
Than it is to measure a small actual value accurately.
Precisely. 0 is a perfect reference. Measuring, say, 0.01 microamps is hard, but seeing the needle at exactly 0, that's easy and very, very accurate. So let's build a mental image. Visualize the 4 resistors arranged in a diamond shape.
Okay, like a kite.
Yes, a diamond or a kite. You apply the battery voltage across the top and bottom corners.
Got it.
And then you place the galvanometer, our detector, across the left and right corners. When the resistance ratios are perfectly matched, the potential at that left corner, let's call it VB, becomes equal to the potential at the right corner, VC.
So if VB is equal to VC, that means there's no voltage difference across the galvanometer.
And therefore?
So no current flows, right? That is the null state you mentioned.
Exactly. That 0 reading, the null state, that is the absolute key to its precision. It tells us the potentials are perfectly equal. Now that we have the basic idea, let us see how insert defines this structure and its principle. Could you please read the definition of the Wheatstone Bridge and the null condition from the source document?
Of course. It says, the Wheatstone Bridge is an arrangement of 4 resistances, R, eros, as shown in the text. The null point condition is given by R eros, using which the value of one resistance can be determined, knowing the other 3. Okay, insert says, null point condition. If the bridge is unbalanced, the galvanometer shows some current. I have a doubt here. How do we prove that VB equals VC actually leads to that formula, R eros R?
A very good doubt. This is where the maths becomes really simple and elegant. You see the 2 arms. The one with RRs on the left and the one with R on the right, they are essentially voltage dividers.
Ah, okay, I remember voltage dividers.
So for the potential at point B, VB, to equal the potential at C, VC, the ratio of the resistances in those arms must match perfectly. If we use the voltage divider rule and we set VB equal to VC, then after some cross multiplication and simplifying, we get the essential balance condition, which is R multiplied by R is equal to R multiplied by R.
The cross products.
The product of the opposite resistors, yes, it must be equal. Hope everything is clear so far. This concept explainer is from ProfSam.com, that is ProfSam.com. Now let's apply this to a very simple numerical example. It will make the concept solid. Suppose we have a bridge where R is 100 ohms, R is 150 ohms, and R is 200 ohms. We have an unknown resistor, R.
Okay.
If we adjust things and we achieve that perfect null balance, what must be the value of R?
We would use the balance condition. R times R equals R equals R times R.
Good. So we set up the calculation. That's 100 times R equals 150 times 200.
So 150 times 200 is 30,000.
Correct. So 100 times R equals 30,000. To find R, we just divide.
30,000 divided by 100, which is 300. So RO must be 300 ohms.
Exactly 300 ohms. See how simple that was. By just making the galvanometer read 0, we calculate the unknown resistance precisely. This technique is extremely reliable.
It is surprisingly straightforward.
And remember, this entire analysis proving that VB equals VC, this is actually a beautiful application of Kirchhoff's rules, which we just studied.
Oh, from the previous topic.
Yes, you can use Kirchhoff's voltage rule on the two loops in the bridge to prove, rigorously, that the potential difference across the galvanometer is 0 only when that ratio, RRO, holds true. It connects everything together. Now let's move on to something very important for exams, the silent killers. These are the common misconceptions that can make you lose marks.
Okay, I'm ready.
Misconception number 1. A lot of students think the Wheatstone Bridge is only useful for measuring a fixed resistance value, like a simple resistor from a box.
But you mentioned it's used for thermometers and strain gauges earlier. That means the resistance must be changing.
Exactly, you're ahead of the curve. What's fascinating here is that the bridge measures anything that changes resistance. That unknown resistor R, it might be a thermistor, its resistance changes with temperature, or a strain gauge whose resistance changes when you stretch it. The bridge is a sensor tool, really.
So it's not just for finding a static R. It's for converting things like strain or temperature into a resistance change that we can then measure precisely using the null condition.
That's a perfect way to put it. It converts a physical change into a resistance ratio. Okay, silent killer number 2. If the galvanometer reads 0, many students think it means there is no voltage or current flowing anywhere in the whole circuit.
I could see why they might think that. 0 current means nothing is happening.
But that's absolutely not true. Voltage is still being applied across the entire bridge. Current is still flowing through REO-ROR and RROR.
So the main circuit's still active.
Yes, very active. The only thing that has happened is that the potential at point B and point C have become the same. So VB equals VC. That's why current through the galvanometer specifically is 0. And the third one, a subtle one, students worry that the measurement is only accurate if the bridge is perfectly balanced to R equals 300,000 or 0 ohms exactly.
Which seems impossible in real life.
It is mathematically impossible. But this raises an important point about why the bridge is still so accurate. It's because null detection is highly sensitive. We achieve balance to within the precision limits of our galvanometer. A good one can detect imbalances as small as parts per million, so we know we are extremely close to perfect balance. That's more than enough for incredible accuracy.
So we get as close to 0 as our instrument can detect, and that's good enough.
Better than good enough. It's the foundation of precision measurement. Now, to help you remember the balance condition, R arrow for life, here is a simple mnemonic. Just remember the phrase, cross products are equal. It should remind you of what you learned for similar triangles in maths.
Cross products are equal. Simple enough.
And our key mantra for the whole concept is Wheatstone Bridge. Balance by adjusting known resistors until galvanometer reads 0, then calculate the unknown.
Adjust, null, calculate. Got it.
And a physical gesture to lock it in. Hold your hands in a diamond shape. The top and bottom are your battery. Your arms are the resistors. Balance is achieved when your pinky fingers, which connect the sides and act as the galvanometer, stop moving, when they achieve that perfect null. All right, let's wrap this up with a 3-point summary for your exams. Summary point 1. The Wheatstone Bridge uses 4 resistors, R arrow, and RO, in a diamond shape to measure an unknown resistance with very high precision. Summary point 2. The balance condition is achieved when the galvanometer current is 0. This means VB equals VC, which leads to the null condition. R arrow is RO. And summary point 3. The bridge principle is highly accurate because it relies on sensitive null detection, not absolute voltage or current measurement. This makes it ideal for converting physical quantities like strain or temperature into resistance measurements. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROF Sam, right?
Yes, ProfSam.com. Thank you for diving deep with us today.